It's just like this. It's like no, I realize it. They were friends. They just like I'm so cool. All right. Look at you all. Are you ready? Yes. It's so sad. Last lecture. Last lecture. I don't know. You might be happy. But you all right, so time me. It shouldn't take more than 25 minutes. And then we will party. We have food. Thank you, Lukman. Yay. And then I got your drinks as well. Thank you. And then I have the prizes for the winners. All right. Okay. So who wants to get started? Nobody. Oh, one more thing. Good job, everybody gets +2 on the final. Everybody. Oh gosh, I'm gonna miss these guys. Who wants to stay for another year and took food analysis again? All right. Let's get going with this. All right, so we stopped here. And here's a cocktail of additional chemicals of concern that could be residue in the food produced during processing or adulterants. So we're going to talk about a few of them. But before we get started, because their presence is random and they're present in very small concentration, so it really, the sample preparation is very important. And then also most of the assays or most of the methods are chromatography coupled with mass spectrometry for enhanced sensitivity and detection and better threshold for quantification. But these are tedious methods, and sometimes in industry, you really want something really quick. So they're always in developing or working on developing methods of detection that are easy, quick, and reliable. So sulfites are of concern because some people have sensitivity to sulfite. So it causes kind of like asthma-related reactions. And sulfites can be present naturally or they can be produced during a processing or added to food for their antimicrobial they act as antimicrobial agents, and also they prevent browning. So they kind of act like a reducing agent against oxidative browning. Okay, so because some people have reactions, we have to put on the label contains sulfite if the content is greater than 10 parts per million. There are so many different methods of analysis, and there's not one method that can capture all forms of sulfite. However, the most common method that I want you to remember is the Mounier-Williams method. So, but what I want you to know is really high level. It measures a sulfur dioxide that is generated from sulfite by acidifying. Adding acid and heat, you can generate sulfur dioxide and it gets oxidized into sulfuric acid. And then you measure gravimetrically or by measuring turbidity. That's what I want you to know. The name of the method, which is the most common method, and it's approved by FDA. And it's basically, you get the sulfite, you use acid to convert it to sulfur dioxide, and that gets oxidized to H2SO4. and then measure gravimetrically or by measuring turbidity. Okay, now there are other methods, but all I want you to know that there is a method that is titration-based, enzymatic, or chromatography. That's it. No more details, FYI, the detail here. Now, nitrites and nitrates are important also because they could form nitrosoamines, which are carcinogens. So it's important to determine their content. They're usually used, sodium nitrite and nitrate, to cure meat. And they're added also, they could be present in water, drinking, and bottled, but there is a legal limit for that. Health concerns, the nitrosoamines are carcinogens, and then a form of anemia can be a result of high consumption. Okay, so the most common method, there are two methods that are common. They are both AOC. One is colorimetric method, and one is a chromatography method. That's all what I want you to know. For the nitrites and nitrates, also we have rapid method. We talked about during mineral chapter, we talked about ion selective electrodes, and then there are test strips for quick qualitative determination. Melamine is an adulterant. It was used without knowing really the consequence. It was just cheating to increase the assumed protein content. But they didn't realize that it really is going to cause kind of damage to kidney and potentially death. So it was added to pet food to increase the protein assumed content, because look at that. You have a lot of nitrogen, a lot of amines. So whether you use DUMAS, nitrogen analyzer, or you use Caldol, those amines can be converted to protein. So they just increase the assumed protein content in the product. So it was in pet food. They also put it in baby formula, which is unfortunate because there were several cases of toxicity and death. So melamine is really a compound used in plastic, so it shouldn't make its way to food, but it was added just to increase the assumed protein content without knowing the consequences. So methods of analysis are chromatography methods with MS, mass spectrometry, running standards. They could be liquid chromatography or GC chromatography, but both require mass spec for identification, correct identification, and quantification. There are methods that are faster, like infrared, spectroscopy, immunoassay, but they're not as reliable as chromatography and mass spectrometry. Bisphenol A, this is the compound that could be in plastic. It mimics our body hormones, some hormones in our body, so it causes health effects, negative health effects, especially in kids, babies, and young children. And it is a compound in plastic, but it's banned. So it's banned, those plastics are banned from being used. And method of detection, either GC or LC coupled with MS. Again, you see a lot of repetition of chromatography and mass spectrometry for almost all of these. This one, there was a case I put here recently, but it's no longer really recently. I should update the wording. But there has been a case where they found it in cereals, and it is ink that was used on the box leached into the cereal. Now, if you notice that when you open a cereal box, what do you see? You see a container inside. So it's kind of like protecting the product from any potential label ink that can go into the product. So it does have negative effects on potentially kidney function. So, and it impacts children as well. So again, LCMS. Furans, these are compounds that are not like added to food or residues. They can be produced during processing, high temperature and in acidic foods. So they can be produced and they're carcinogens. So they, again, they're volatile. So you can use headspace GCMS for detection and quantification. Acrylamide is another one that is produced due to processing, like deep frying of potato chips, is one where your asparagine specifically react with the carbonyl group, Maillard reaction, and that could, an end product could be acrylamide, which is carcinogen. Again, chromatography, mass spectrometry. Benzene can be formed if we have ascorbic acid and benzoate in a beverage. This can cause benzene formation and it's carcinogen. It is volatile, so headspace GCMS is used. This one is specific in soy hydrolyzed product, soy protein hydrolyzed product. It is formed when we use acid hydrolysis and the acid reacts with residual lipids and you get this compound that is also a carcinogen and a genotoxin. It is volatile, so GCMS is used. Last one here is perchlorate. This can be present naturally in the soil or can be generated due to certain climatic conditions. It impacts our thyroid gland, so can result in hypothyroidism. It can be found due to contamination from the soil in water or milk and lettuce. These are reported cases. Iron chromatography, MS. So if you notice, most of them is chromatography and mass spectrometry. This is a table where it's in your chapter 33, and that's would be a good one to study. If you don't want to learn anything I talked about or all the slides, if you look at this table, that's basically would be good to know. If I ask you about any of these compounds, like how did it make it to food? So if it's antibiotic, well, they gave the cow antibiotic and very close to milking or very close to slaughter, it remained in the food or no, in the meat or no. Why is it concerning? What type, an example of food, and what is the method and detection? So this would be the information for most of these compounds of interest. That would be what I would ask you about, similar to the question in the review packet, but it would be asked in a different format. All right. Any question about what you want to focus on here? All right. So your most exciting lecture topic, this one. Most exciting. Why? This is everything filthy that could come into your food. We call it extraneous matter. Stuff that shouldn't be in food, but it's unavoidable. The amount of insects we eat every day. Huh? Yeah, really. Yes, it definitely increases your protein intake.
Like how many grams do you think a day?
Like, I'm getting to that. It's coming. How many parts of insects, rodents' hair is allowed? Hair is protein, you know that, right? Yeah. We'll get to that. But so those extraneous matter is different than the residues that we talked about and the contaminants that we talked about. These are just things that are not supposed to be in food, but there is no way around it. Whether it's insect parts, rodent hair and excreta, bird feathers and poop. So these are things that I'll tell you why they're not very much avoidable 100%. And then there are the non-organics, so stones, sand, dirt, metal, glass. Sometimes we get those also in the food. All of this is extraneous matter. Why are you super excited, Emma? It's Ali's fault. It's always Ali's fault.
Human hair.
Huh?
It doesn't exist, so we have to the PDCast of human hair.
Oh, the PDCast of a human.
It hasn't been determined yet, so. Yeah.
Interesting.
I know someone with it. That's in labs.
Write that down under something. We never we never looked at the PDCast of human hair or rodent hair for that matter. Okay, so insects in some cultures are delicacy, so they're food. Some are edible insects. Not all insects are edible, but some are edible and they are eaten in different cultures. So it's not always a bad thing, but in other cultures, it's icky. And there are all sorts of bugs that can end up in your food, especially when you're like on going to harvest. Of course, there's all sorts of insects that you're harvesting with the grain. And then you have the storage facilities. I'll show you a couple of pictures, and then transportation. And then during processing, at every stage, you might get insect contamination in your food. So harvesting, so look at these little insects that are living on the grains, and they get harvested with the grains. So parts of it, they might be cut into pieces, but. And then you have the storage facilities where you can see little rodents that might make it to the grain storage area, unavoidable. So basically we have the Food, Drug, and Cosmetic Act that says that food can be adulterated if containing filth, putrid, or decomposed matter. So there is this, you learned about it in quality, good manufacturing practices to avoid as much as possible the contamination. So thorough inspection of raw material, monitoring of food processes operation, but it's unavoidable. You cannot eliminate it 100%. That's why there are defect action level, which mean above which we consider them defective. So look at 30 insect fragments and 1 rodent hair per 100 grams of peanut butter. That's the defect action level. So if you have 28 insect fragment and 0 hair, you can still call the peanut butter good. So if you like peanut butter, think about how much insects you're consuming. All right, and look at the flour. If you eat bread and enjoy bread, every 50 grams of flour, like 50 grams of flour, have 75 insect fragments and 1 rodent hair. Above that is a defect. Below that, you're all good. Yes?
So does that mean that the insect fragments account for some of the protein content on like the standard?
Oh yeah, absolutely. It might increase the protein content in your flour.
So if you wanted to increase it to get to 75 insect fragments.
You can reach 75, but not more. It will be defective after that. In 50 grams, huh? Yeah.
That sounds good.
Well, that's the problem. That is the problem with insect protein right now. So there are regulations on this, but then what about insect protein concentrate that is becoming an ingredient? How do we label this and how we differentiate it from defect action level? It's a dilemma. Oh, I have a joke for you.
Tell us.
This is Luther. He investigated the sudden increase in rodent hair in peanut. There's a barber over there. And then this one, hold it. this one only has 7% insect parts.
That is. I'm like, at least 10.
All right, so these are terminologies that you would usually hear when we talk about extraneous matter. Filth. So filth is anything animal related. So contamination, objectionable matter. So heavy filth is like sand, soil, insect and rodent excreta pellets can be separated by sedimentation. And then we have light filth that is usually hair, insect fragments, feather parts. And then there is sieve filth, filth that you can separate by just sieving it from the ingredient, flour, spices, what have you. So these are terminologies that will come up. So there are different methods, but there are concerns because sometimes it's subjective. And a lot of these methods is based on counting under the microscope. You may or may not know or realize certain parts. Some parts of the insects are very, you can tell that this is an insect part, but sometimes you have a fragment. If you don't have experience, you wouldn't know if this is an insect fragment or not. And a lot of the methods have a lot of transfers. So you might lose some particles of those filth, and then that you will underestimate. Also, most of the methods are based on count. So if you have one whole insect or a part of it, it's counted as one.
Wait.
Yes.
So that's why I have entire insect.
Yeah, you can have the entire insect and it's considered one part. So that's kind of concerning, but again, think about your protein intake. All right, so foreign matter, this is an official method of analysis. Usually for condiments or spices, so it is very simple. You run your spices through particular sieve with mesh number 20, and then you just measure, not measure, count under the microscope. Very simple. So heavy filth is mainly anything that can sediment. So you would you have several reagents that you would use, and then you filter. You either ash and get the weight of the ash of the filtrate that stayed on the filter paper, or count under the microscope. So this one uses a specific kind of flask called Wildman trap flask. Wildman is the guy that came up with it. So what it is you digest the sample. So this is for light filth, which is insect fragments and rodent hair in flour, rye flour. So you use several digestion reagents, and then you would use oil, and then you have the aqueous, and then you get this kind of a stopper thing that you lifted up to the top, and you trap the oil with all of those light filth in it. And then you filter and you look under the microscope and count. This is pretty much similar, but instead of using that Wildman trap flask, you use a separatory funnel with aqueous and oil. And you separate, usually your filth, light filth will be in the oil, they're lipophilic. And then you take that filter, count under the microscope. Here are your wonderful larvae in your kernels. So it's unavoidable. Huh?
Your timer.
What, is it time?
Yeah.
I'm almost done.
Speed.
Yeah, give me a minute. All right, so these are larvae. You would see it with X-ray, and then you count how many kernels are infected. And there's like 32 kernels in 100 grams are allowable to be infected. So other techniques, so other than the X-ray to detect insects, you can measure uric acid, which is present in urine. So it will determine if you have any excreta in there. ELISA for insect proteins, specifically NIR to determine the later stages of insect, and then microscopy for all sorts of non-organics, so glass, plastic, and other contaminants. So avoid, this is the last slide, to avoid or have a prevention, you would monitor by X-ray. You can then break and aspirate. So if you have insects living larvae inside the wheat, you can crack it, aspirate by air, and then you can get a lot out of it. And then air floating, so you would put them on a belt that have holes in it, and then you have air blowing from under. So the light seeds or kernels will like kind of float, and then the dirt, the stones, metal will just stay on the belt and get separated. And then you use magnets to get any metal out. And on this happy and non-disgusting note, we end the lecture. Good job, everybody. All right, so I'm gonna stop recording and I'm gonna turn it to Emma and Allie for the Kahoot. Let's go.
Wait, no, not yet, not yet, not yet.
Oh, when do we want?